Here's SAC 105. If you haven't read it already, please pause the WinCam presentation and take a read. This is a conservation of angular momentum problem because the system of man plus disk has no external torque exerted upon it. So conservation of angular momentum problem, we start by drawing a before and after picture. To start with, we've just got a man standing on a disk. Nothing is spinning. In the after picture, the man has jumped in such a manner that he is indeed spinning. Counterclockwise as viewed from above, so around this way. With an angular momentum, we don't know how fast he's spinning or what his moment of inertia is, but his angular momentum is L counterclockwise, and this is going to leave the disk down below, so he's off of it. I don't know if we can put some lines in there indicating he's up in the air off of the disk. Actually, I think I'll draw the disk completely below him to make that more obvious. So I'll put the disk down here, and it's going to be rotating now in the opposite direction. To the direction which he's rotating, with some angular velocity, I'll call it omega, and that's what we're looking for. So initially, the total angular momentum is 0. Nothing is spinning in the before picture, and the after picture stuff is spinning. The man is spinning and the disk is spinning. Now I'm going to write conservation of momentum instead of using L is equal to L prime, especially since I got the symbol L over here in the after picture. I'll write L before equals L after. This represents the total angular momentum before and the total angular momentum after, and I'm going to specify what I mean by a positive angular momentum, counterclockwise as viewed from above. So the total counterclockwise angular momentum as viewed from above in the before picture has got to be equal to the total counterclockwise angular momentum as viewed from above in the after picture. Over here, by inspection, it's 0. Nothing's spinning, no angular momentum. Here, we've got a combination of the angular momentum of the man, counterclockwise, plus the angular momentum of the disk, counterclockwise. We've got to work on this a little bit because the disk is actually spinning clockwise as viewed from above. You try it in order to get yourself spinning counterclockwise. If you're standing on a disk when you jump up, the disk is going to be spinning clockwise. This will come out anyway, but I'm going to consider the disk to actually be going around clockwise, and I want to insert that in the equation explicitly. So positive value for L for the man means counterclockwise. Now in my picture I have defined clockwise as a positive omega, and therefore the angular momentum of the disk is minus, angular momentum of the disk counterclockwise is minus I omega, where omega is clockwise. So in general, it's I times omega counterclockwise, but minus omega clockwise is the angular velocity counterclockwise. All right, go ahead and solve that for omega. I'll just add I omega to both sides. So I omega is equal to L. This is interesting. It almost looks like definition, but this is angular momentum of the man, and this is angular velocity of the disk. And in fact, the angular velocity of the disk turns out to be the angular momentum of the man divided by the moment of inertia of the disk. And of course, we got to indicate the direction explicitly. Implicitly, we've stated, we've solved for what omega is, and we've defined omega as being clockwise. Positive omega is clockwise, but we should state explicitly that our answer is clockwise as viewed from above. Viewed And that does it for SAC 105, problem number 1.